Johnny here with Simpson Math. In this video, we'll be solving exponential equations, and we're going to start off maybe pretty simple, but then we're going to be using logarithms to solve these. So just what is an exponential equation? I've got this equation because of the equal symbol, and then my unknown value is in the exponent position. So my x variable is in that power position. So we call this an exponential equation. And I want to solve it, meaning if there's some number that makes this equation true, I want to know what it is. And if there's more than one, I want to know all of them. So this is saying 3 to what power is going to give me 81? And some of you may just know the answer, but one way to solve exponential equations is to make the bases match. We know if some base to the m power is equal to that same base to the n power, then just using logic, if these bases match, then so too must the exponents. Then that m power must equal this n power. So what I would like to do is rewrite this equation with matching bases. 81 happens to be a power of 3. On the right-hand side of this equation, I'm comfortable saying 81 is the same thing as 3 to the 4th power. Oh, okay, yeah. If my bases match, then so too must my exponents. So I'm comfortable saying x equals 4. Cool. So some exponential equations, we're just going to set these, make sure that the bases are equal to each other, make them, and then the exponents will be equal to each other. And that's how we can solve the equation. Let's try something like this. I have 3 being raised to 2x plus 1, and that is equal to 27. Again, I'd like to maybe try to rewrite my bases so they are the same. 3 is pretty basic, but 27 is a power of 3. That's 3 to the 3rd power. So I'm going to rewrite the right-hand side of this equation as 3 being raised to the 3 power. Base 3 raised to 3 power. If my bases are equal, then I can set my exponents equal to each other. I'll have a lot of students that they think there's some sort of reduction going on here, some sort of math. This is just logic. If this is an equation and it is truly equal and the 3's match, then those exponents must also match. So this is just using logic. But now I have a linear equation that I can solve. I can move the 1 over. 2x equals 2. Solving by dividing both sides by 2, I get x equals 1. I have solved this exponential equation. Let's amp up the difficulty level. I have 4 to the x set equal to 32. 4 seems pretty basic. 32 is not a power of 4. Any thoughts? Well, 4 and 32, those are both powers of 2. So I'm going to rewrite both of them. 4 is the same thing as 2 squared. That was being raised to the x power. 32 is 2 being raised to the 5th power. Now, if you take a power and raise it to a power, you're just going to multiply. This is an old exponent rule. B to the m raised to the nth power is b to the m times n. So I'm just going to rewrite this as 2 to the 2x equaling 2 to the 5th. Equal sign, bases match, my exponents therefore are equal. So I claim 5/2 is the solution to this exponential equation. All right. How about 5 to the 2 minus x equaling 1 over 125? Well, 5 seems pretty basic. Now 1 over 25, that is some exponent stuff going on there. 5 squared is 25, 5 cubed is 125, but 5 cubed is 125 normally. How do I get the 125 down below? That would be a negative exponent. So this must be 5 to the negative third power. So I'm using exponent rules to rewrite 1 over 125 as 5 to a negative third power. Negative exponent rules. Bases are now matching. Exponents must be equal. Solving, I get 5 equals x. Let's do one more of these. 7 raised to a quotient power x minus 2 over 6, and that's equal to the square root of 7. Well, they look similar, but I need to see a power. So I'm going to rewrite the square root of 7 as 7 being raised to the what power? Huh? 1/2 power. 7 to the 1/2 power is the square root of 7. My bases match. Now I can just almost ignore them and set my exponents equal to each other. X minus 2 over 6 will be equal to 1/2. If my bases match, so too do my exponents. This is just a linear equation. I should be able to solve for it. If I multiply both sides by 6 to get rid of the denominator, I get 3 on the right. Adding, I get 5 again. X equals 5. All right, so those examples of exponential equations, all of those, we were able to rewrite the bases to be the same. Maybe we had to know some exponent rules. Maybe we had to manipulate both sides. But we were able to take those bases and rewrite them as the same base. Those are pretty simple and fun, but there are harder ones out there. Let's take a look at something like this. I have 10 to the x power equals 8.07. There's no way I'm going to be able to rewrite these bases as the same base. That doesn't make sense to me. Now the question is asking 10 to what power gives me about 8? I could give you a good decimal estimation. I know 10 to the first power is 10, bigger. 10 to the 0 power is 1. So I got 0 is giving me 1. 1 is giving me 10. So it's somewhere between 0 and 1. That's my estimation. Yay. Okay. So to solve this type of exponential equation, I have 2 options. I'm going to do one option in black and one option in pink. Option 1. We are dealing with exponential equations. So there's some sort of exponential expression. One thing we can do is isolate it, get it all by itself on its side of the equation, and then we can always rewrite it in logarithmic form. So I'm going to, put little steps here. Isolate exponential expression. Then I'm going to rewrite in logarithmic. And then maybe there's some simplifying to do. And you should be able to solve at that point. So in black, let's just do that real quick. The exponential expression is already isolated. The 10x, that base and that power are the only thing on that side of the equation. So check mark. I'm going to rewrite it in logarithmic form. Oh yeah, I can do this. If I have some base to a power equaling something, I can just rewrite it using the definition. This is now log base 10 of 8.07 equals x. Simplify if I'm able to. I've already solved this thing. X is equal to log 8.07. I don't actually even need the base 10 because log has an understood base of 10. We did it. This is this is the exact value. So the true answer is going to be some decimal that we would have to approximate. If I were to plug this into a calculator, it's some number between 0 and 1, but it's not a pretty fraction. It's some decimal thing. So I don't want that. I want the exact value, log of 8.07. That's it. Now option 2, I'll write in pink. It starts off the same way. We need to isolate the exponential expression. Then we can do something with these logarithms that we may not have ever done before. Back in like square root days, if I have an equation, I can take the square root of one side of the equation as long as I do it to the other side of the equation. The same is true for this operation of logarithms. I can take the log of both sides of the equation. Now typically when we do this, we want to use the natural log. Just take the natural log of both sides of the equation. Now because this example happens to have a base of 10, it's very fortunate, maybe we should take the log of both sides. But I'm in my notes here for steps, I'm going to say take natural log of both sides. Maybe in parentheses I'll say log if you see 10 or multiple, like if I saw 100, I would want to use log. But any other number, 7, 3, e, pi, 13, every other number, the natural log is what I would typically want to play with. But because this has a 10, I'm about to use a regular logarithm. Then you should be able to simplify. Because logs are involved and there was a power to begin with, we'll probably use the power property to simplify. That's the one where we can take the powers and write them out front as a coefficient. And then we should be able to solve. So both options have about 4 steps. The option 1 should be quicker for all of today's examples, but I would like to use both options multiple times. This is a skill that we will be using later in your next math courses. And this is the time to practice it. So let's do it. I'll just rewrite the problem. 10 to the x equals 8.07. We've isolated the exponential expression. And now what I would like to do is take the log of both sides of the equation. It's legal to take the log of the left-hand side of the equation, as long as you also take the log of the right-hand side of the equation. Again, I would probably prefer the natural log, but because I see a 10 somewhere in the equation, I'm going to use log, base 10. These logs have an understood base of 10. Now this is one of those inverse properties of logs. This on the left-hand side says the understood base 10 to what power gives me 10 to the x power. Well, that just simplifies to x. Or, if I had followed my steps exactly, it says use a power property. So, I have log of 10 to the x power. This x can be rolled off the log using a power property of logarithms. So I have x times log of 10. Log of 10 is just 1, so x times 1 is x. Either way. All right, let's do it again. Another example. Let's take 9e to the x and set that equal to 107. I want to know what x value will make this equation true. E is just that irrational number 2.71828, blah, 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 blah. So I'm not going to be able to take E and 107 and somehow make those bases match up, be the same base. That's not going to work out. So I think I'll try option 1. And that is isolated. Right now, my base here is E and the exponent is x. That 9 coefficient needs to go away. I'm going to divide both sides of the equation by 9. I have isolated the exponential expression. Now I can rewrite this in logarithmic form. I have a natural log with base E of 107 over 9, and that's equal to the power x. I'm just using the definition of the logarithm to rewrite exponential form as logarithmic form. I'm done. 7, 8. I was looking to see if that simplified 107 is not divisible by 9. So x is completely by itself. I know what it is. X is the natural log of 107 over 9. This is the exact value. If you were graphing this or needed a decimal approximation, you could throw this into a calculator. You could probably just try to mentally estimate what this is. 9 would go into 99 11 times, 108 12 times. This is almost 12. And this is asking e to what power gives me 12? I don't know that. E squared is about 7.4, I know that. So it's bigger than 2. Decimal. If you need a decimal for whatever reason, bust out a calculator. Okay, now, while we're on the same problem, I'll do option 2. And that is, again, isolate the exponential expression. So I still need to divide both sides by 9. But here, I'm going to take now the natural log of both sides. So the natural log of e to the x equals the natural log of 107 divided by 9. On the left, I see one of those inverse properties. So this is just x equals natural log 107 over 9. Same thing. Let's try something like this. E being raised to the 4x minus 5 power minus 7, and that's equal to 11, 2, 4, 3. For both options to solve these equations, I need to isolate the exponential expression. And right now, there it is. The base is e, the power is 4x minus 5. The minus 7 needs to go away. I'm going to add it to both sides of the equation. (11,250). Now, I'll just simply rewrite this in the logarithmic form. I have the natural log, understood base e, of 11,250, and that's equal to the power 4x minus 5. Well, I'm trying to get the x by itself. So now it's got this like linear feel to it. I'm going to add 5 to both sides of the equation. Don't be confused. This is not going to be the natural log of 11,255. 11,250 is the argument of this natural log. If I add a number over here, those are unlike terms. It's like saying the square root of 3 plus 5. I cannot call that the square root of 8. Those are two different types of numbers. They're unlike. Last thing to do is divide both sides by 4. We found the exact answer, the exact value. Option 2, just very quickly, same thing. I would take the natural log of both sides. Then that would just go away. Oops. I entered the natural log over there. Yes, exact same process. So in black, I was rewriting in logarithmic form. In pink, I was going through this, maybe a new process of evaluating both sides of the equation, taking the natural log of both sides. Let's do something like this. Five to the x minus 3 equals 137. I don't have a 10, I don't have an e. Let's see what to do here. All right, the exponential expression has been isolated, check mark. I'm now ready to rewrite it in logarithmic form. I'm going to say log base 5 of 137 is equal to the power x minus 3, using the definition of a logarithm. Now, what can I do? Oh yeah, just simply add the 3 over and I'm done. X is equal to log base 5 of 137 plus 3. Easy. Let's go through the motions of taking the natural log of both sides. I'll take the natural log of 5 to the x minus 3 equaling the natural log of 137. Well, here, nothing pretty simplifies. It's not an inverse property, but I can use the power rule, or the power property of logarithms to roll the power off the log. So this x minus 3 becomes a coefficient. All of x minus 3 is being multiplied by the natural log of 5, and that's equal to the natural log of 137. I think I'll just put all these arguments in parentheses so I don't make a mistake. Now I'm trying to solve for x, so I'm going to divide, because this is being multiplied by this number ln5. So I'm going to divide both sides of the equation by ln5. Now this may, you may think the old like quotient property of logarithms, but that's not what's going on. It's not the natural log of 137 over 5. So I cannot apply like that quotient property. This is just the natural log of 137 divided by the natural log of 5. Some number divided by another number. They're not all that pretty. To get the x by itself, I simply add 3 over. Add 3 over. This is another exact value for our solution. The natural log of 137 divided by the natural log of 5 plus 3 works. If I were to plug these into a calculator, they'll give me the same decimal approximation. All right, that's how we handle exponential equations. I'll see you in the next video where we handle most likely logarithmic equations. See you then.